So here today I'm going to talk a bit about the Scikit-learn machine library and recent development and ongoing works. So I will first introduce the Scikit-learn machine library very quickly for people who don't know it, and then introduce the new things and future work. So Scikit-learn is a predictive modeling library. So the goal is to make prediction of the outcome of repeated events by extracting the structure of the historical record. So this is traditional supervised machine learning, or unsupervised also. And the tools that we use are statistical tools that tries to turn a summary of the training set into some kind of executable models, a Python program. And you can see it as an alternative to hard-coded rules written by experts on a specific domain of interest. But in practice, it's suitable in the cases where you need to compute many small predictions, and by small I mean predictions that individually do not bear a big cost in case of individual mistakes, but on average you want the error rate to be as low as possible for scientific value or business value. So the typical kind of data that you can analyze with Scikit-learn is this kind of tabular data, business data. So in this case, it could be a real estate agency where you have the log of past transactions with different columns that we call the features, with values that can be categorical or numerical, like integers or floating point values, or also other kinds of data like dates. And typically, you have a target column that you are interested in modeling, and you want to find a statistical relationship between the target variable here, the price of a house, with respect to the other attributes that have different types. And the goal is, once you have extracted this statistical summary, this statistical relationship, to build a model that can answer the question marks when you have no customers who come to the real estate agency to give an estimate, possibly with some kind of a confidence interval. For the estimation. So the vocabulary that we use for this is that the attributes of this tabular column database are called the features of the model. There is a target variable that we want to predict, and the data is splitted, the records are splitted between the past and the future, with the training samples, the training set, and the test set where we compute the prediction. And ideally, when we receive the ground truth value for those, we can evaluate the generalization ability of the model by comparing the predictions and the true labels that we collect in the future. So Scikit-learn can help you do that. It's a library of many hundreds of classical algorithms for data science and machine learning. So our goal is not to do research on machine learning, is not to advance the state of the art, but it's to implement the stable part of the state of the art, to make sure that usable algorithms are even more useful by being easy to use, basically. So it's an open source project. There is a community of hundreds of contributors per release, and there are core developers, like regular maintainers of the project, in Australia, in China, in France, in Germany, and the USA. And they were also in other countries in the past. And it's implemented in Python and a bit of Cython. Cython is an extension of Python for a compiled extension of Cython with a syntax, programming language syntax that looks like Python. And it relies a lot on external libraries like NumPy and SciPy, that provides very efficient ways to do linear algebra operations and optimization. One of the main selling points of Scikit-learn is that we provide a very homogeneous API. All the statistical tools that we provide have the same method. To train on the data, there is a method called fit, and then you can compute prediction with predict, or alternatively, you can transform the data into a new space using the transform method. So it's very easy to swap different kind of algorithms from different families to see which one is the best for a specific problem. We also provide additional tools for model evaluation, computing the accuracy on a test set, for instance, or using a procedure that is called cross-validation. For model selection, finding the best parameter, how to tune the parameters of the model, and also to build ensembles by combining the predictions for several models to get better predictive accuracy. And finally, we estimate that we have 600,000 monthly active users because those are the people reading the documentation online. So what is new in Scikit-learn 0.20? We put a lot of effort in the last release to make it much easier to have more flexible feature engineering. In the table before, you could see that there were different kinds of data types, categorical variables, numerical variables, dates, and so on. And here, the main effort of this release cycle was to make it easy to have heterogeneous model using this tool that we call the column transformer that can apply transformation for different kinds of columns. And the kind of transformation that we can apply is a categorical variable encoding like ordinal and one-hot encoding, transformation for numerical variables like binning and power transformation for scaling. And we can also make it possible to apply a transformation on the target variable if it's a continuous variable. There are also improvements in other models like early stopping for classifiers, also improvement in the documentation and improvement in the ability of the library to better use parallelism, especially on distributed computing infrastructure such as a Dask cluster. So here is a bit of code to show how the column transformer works. We start from a CSV file that has heterogeneous data. So it's the Titanic data set from Kaggle. We isolate the target variable that we want to predict, whether or not a passenger has survived. And then we consider for all the other columns whether or not they are numericals or categorical variables. And then we define two pipelines that will be combined into a single column transformer that we call the preprocessor. So for the numerical variables, we will map it to the first pipeline that does imputation of missing values using the median, and then do binning with 5 bins for each of those variables. For the categorical variables, we do a different imputation strategy if they are missing variable, using a constant value flag that says it's a missing variable. And then we do one-hot encoding. Once we have this preprocessor, we can pipeline it again with the logistic regression, the classifier, using the Saga solver in this case. And here you can see that it's very easy to use this very complex pipeline that was defined with just a few lines of Python, and to make it able to run into a cross-validation procedure to have a sound estimate of the validation accuracy of the ability of the model to generalize. And so here in just 30 milliseconds, we will have a tenfold cross-validation score for this classical data set. So one of the transformations that was newly introduced is the binning. It's interesting because if you have some data that is non-linearly separable, for instance, here the goal is to predict the green and purple points, and if the greens are in the middle, as on the second row, a linear model on the first column of the model is really bad and cannot separate the two groups. But if you apply the binning preprocessing before applying logistic regression, you see that the linear model has gained in expressive power and now is able to rival the performance of non-linear models like gradient boosting and support vector machines. So it's a very fast preprocessing that turns fast linear models into more expressive and powerful models. So it's a very interesting strategy. We also have other tools that kind of normalize numerical variables, like parametric power transformation, like the Box-Cox transform and the Yeo-Johnson transform. And there is also a non-parametric transformation, which is called the quantile transformer, that does the same if you have a lot of data. It's also interesting. So I would like also to talk a bit about Jobleap and Dask. So Jobleap is the backend that we use for parallel computation in Scikit-learn. By default, it can use thread or multi-process Python process on a single machine. But what we've changed in this release is the ability to first replace the default multiprocessing backend by something that is more robust, that works better without crashing third-party threading runtimes like OpenMP and such. And secondly, the ability to unplug the backend and to replace it by a connection to a cluster computing infrastructure, such as Dask distributed. And this is even more important if you have a large data science team that shares some compute resources and you want to mutualize the machines and use them when they are available and scale as much as possible. But don't waste the machines where you're not using them by releasing the resources. So we can use Dask for this, and it can run on Kubernetes, Hadoop Yarn, or HPC infrastructure. And there is also a sister project, DaskML, that also has some experimental adaptation of Scikit-learn tools to run on a very large volume of data in out-of-core manner. All right, so this is how you would use Jobleap from this environment. So here you can see that there are two CPUs. Here we're going to predict the price of a house in California from a standard benchmark data set. So first we split the data set between train and test. So to take 10% of the data set as the test set so that we can evaluate the accuracy of the model. Then we want to train a random forest to predict the price. But this random forest has many kind of hyperparameters, and we don't necessarily know what is the best value for those hyperparameters. The number of trees, the depth of the trees, the max features that we consider for a split in a random subset of the features. So to select the best value, we will have to select a combination of those three parameters. We can do an exploration automatically to try many kind of combinations at random and pick up the best one. This is called the randomized search strategy. Here we do 5-fold cross-validation to compute the cross-validation score and consider only one random iteration on this machine because it's too slow. And you can see that by default it's using a Jobleap and run in parallel processes, and it takes 10 seconds to just evaluate one combination. And then we get the result. We can load it in a pandas data frame and see that the test explained variance is 79%. We can see the parameters of the model that was explored, and we don't really know if it's good or bad, but what we can do is compare the validation accuracy with the final test set accuracy. We see that they are approximately the same, so this is fine, but it's too slow. So how to make it run faster? Here we're going to use Kubernetes, so a cluster orchestration tool, and use Dask to run worker on that cluster. So actually my Jupyter Hub here is running on the cloud on a Kubernetes cluster. And what I can do is use Dask Kubernetes to tell that I need additional workers. So here you can see in the bottom right that when I executed this in my environment, automatically the additional workers were spawned and provisioned dynamically on the cluster, on the cloud. And also Dask provides a diagnostic page to see the state of the computing resources. So here there is nothing happening, but we can see that the workers are connected. Those are Python processes. By default, they use a very little memory, like 40 megabytes. The CPU usage is very low, they don't do anything. And we also have an aggregate view of all the cluster resources that are being used here. So if I go back to my analysis, the only thing that I need to do is first to connect my environment to the workers using a client, and then to register Jobleap to use the Dask backend. Instead of using the single machine processors, I will tell the Jobleap, whenever you have something to do, connect to Dask and schedule the work on Dask. Because Scikit-learn is using Jobleap, in turn, we can do this kind of embarrassingly parallel evaluation on the cluster. And so as soon as we run this, here we say for 10 evaluations, you can see that everything is shipped onto the cluster, and the cluster is actually dynamically adapting its sizes, provisioning even more workers because it could saturate the existing one. And here it's kind of complex to see the visualization because there is actually nested parallelism where cross-validation is run in parallel that calls into random forest that also runs subtask in parallel, and everything is spread onto the workers of the cluster and can use all the CPUs available. When we come back to the analysis, we see that it's completed quite quickly for a lot more computation. And then we have interesting results because then we can find a much better model, like 2% explained variance better. And we can see what are the important parameters that were explored. So it's important not to limit the depth of the tree. If you don't limit it, it's better. If you use shallow trees in this case, you have a very poor results. The explained variance is very bad. So we can gain some insight on how to best configure our model. So finally, what is interesting with this approach is that here you see we have a lot of workers running on a cluster for our interactive development session. As soon as we interrupt and restart this kernel, this is connected to Dask, and this will automatically shut down all the workers that were provisioned specifically for this analysis. So it releases the compute resources for all the other data scientists in the team. So this is just an overview of new things in Scikit-learn. There are many, many more, and actually I could not zoom out enough in Firefox to see the full change log. Imagine there are at least 3 other screens of new changes and bug fixes and improvement in the last release. Many contributors for this release. So thank you to all of them. This was also the opportunity to fix issues with upstream projects, like the standard library of Python, and optimizing the memory consumption of NumPy, and evolving the standard library of Python to make this optimization possible. So this is still ongoing work, but we have made significant progress. Also, nowadays, we are also starting to work on better leveraging low-level construct from OpenMP and direct blast access in recent version of SciPy. And this makes it possible to accelerate significantly K-means algorithm based on the feedback that we got from François Fayard and engineers at Intel. And the first results that we can see is that when we chunk the data in a specific size, we can see that we can be very efficient in the cache, CPU cache usage. And the orange line here is the performance of the new version of K-means in the master branch, in the pull request of Scikit-learn compared to the master branch, which is significantly slower. And we can also compare to an Intel optimized version, and it's very similar, especially if you use the Intel compiler, you can reach a very similar speed. We are also working on a significantly more performant gradient boosting machine. The goal is to have the same kind of performance as the LightGBM library, but with a more Pythonic implementation. And we are getting closer and closer to that in an experimental project for now. And the goal will be at some point to integrate it back into Scikit-learn. And this is collaboration with Nicolas in Columbia University. So we are using Numba for that. So it's interesting because Numba, you can write a very simple Python code. So this is pure Python that works on a NumPy array. It's an algorithmic loop that is not really linear algebra. So you cannot use NumPy to make it work fast. Even though those are NumPy arrays, the operation that we do on them is not fast by using the NumPy function. So with Numba, what you can do is put this annotation, and then automatically it will analyze the Python code and generate native code and compile it with a LLVM, the LLVM just-in-time compiler. And furthermore, you can also tell it to do the loop in parallel, and it will run on several threads. And so with very little modification in the code, you can get a good scalability on multi-core machines. So this is interesting. We don't use it yet in Scikit-learn, but I would advise you to have a look if you need to write this kind of code. It's very little overhead, and it's a lot of flexibility, so it's a good trade-off, I think. So finally, I would like to thank the partners from the INRIA Foundation Scikit-learn initiative, who will help us support and make this project more future-proof and improve it over time. And we just started this collaboration, so we are really excited about this. Thank you very much for your attention.